First session before the break. I'm David Abrahams, and our first speaker is Michael Marder from the University of Texas at Austin, and the title is that. So over to you, Mike.
Thank you very much, and thank you to the organizers for insistently inviting me. It's been a great pleasure to hear about the recent developments in the mathematics of this subject, one which I've used without knowing much of the theory or current development for a long time. I'm not sure if there's anyone else here from the physics department. Anyone else here from the physics department? I'm from the physics department. Anyone else? All right. So this is proof that the conference is moving from the purist theory towards application. That's the point at which you bring in a physicist to indicate that change. And so I am going to discuss contexts in which the Wiener-Hopf problem has been used. I don't believe I will have any technical advances whatsoever to announce, but I will report on numerous cases in which I have employed the method, and perhaps it will give some of you ideas about cases in which advances could be of assistance to those of us who make use. So the topics I will discuss will be the following. First of all, I will make the case that fracture is a subject that is profitably studied at the atomic scale. I'll talk particularly about the contributions to this topic of Leonid Slepyan, who is quietly sitting right over there. I'll introduce very quickly the simplest context in which the Wiener-Hopf method can be employed, and then I will make use of the method to solve a number of paradoxes in the continuum theory of fracture, notably behaviors of cracks along interfaces and the existence of supersonic cracks that were thought for a long time not to be allowed to exist at all. So that's the outline. Now, I need to make the case for connecting atoms in fracture, so let me begin by quoting one of the great physicists of the last century, Richard Feynman. If in some cataclysm all of scientific knowledge were to be destroyed and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis that things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are at a little distance apart, but repelled upon squeezed into each other. The historical path to learning that this sentence was true was a very long one. The first suppositions that our material world is constructed of atoms go back to classical antiquity, but quantitative attempts to assess the dimensions of atoms and the way they were hooked together took a very long time. The first time I'm aware of anyone attaining an estimate of the size of an atom is 1773. Ben Franklin took approximately a cubic centimeter of oil and put it on a lake, and noticed that the waves were damped over approximately an acre. So if you do the rough math there, you'll find that he took 10 to the minus 6 cubic meters of oil and put them on 10 to the 4 square meters, and that gives you instantly a dimension in the order of 10 to the minus 10, which is of course the right order of magnitude. And that was one of the early indications. Many other early indications existed without giving any indication of the dimension of the atom. One of those was fracture, and fracture was extremely important. Here is the way that fracture entered. There were known to be objects called crystals, and there were museums devoted to them, and if you dropped them on the ground, then they would break, and the faces had geometric regularities to them. So how could this be? What could explain the geometrical irregularities in the faces, the laws of crystal habit? In 1801, there was a treatise published on this topic by Wiener-Hopf. This is a diagram from it, and I believe it is the first indication that someone had thought about the way that atoms, and their dimension was still essentially unknown, could be arranged so as to explain the faces of a crystal. And so that's the first, I believe, the first historical diagram illustrating this idea. Now, the thing that I want to emphasize is that this marks fracture as a process that is able to convey information from the microscopic scale, no matter how far down it may be, up to the macroscopic scale. And therefore, some aspects of fracture will never be captured in any continuum theory and will always be sensitive to atoms. That's not to say all aspects of fracture are like that. Indeed, as we'll see, the 20th century theory of fracture has completely been dominated by continuum theory. But some information was always able to survive that and pass up. And historically, that was extremely important. Amongst other things, this led into group theory because the study of the symmetries led to the space groups. The space groups were an integral part of the development of group theory. So this was both important for the foundation of 20th century science and also for the foundation of 20th century math. So here are some of the essential points. Fracture is a process that connects microscopic and macroscopic scales. If you take a centimeter scale sample and you break it, then you're connecting 8 orders of magnitude in space. There is no continuum limit that can describe the process once you go down below the level of the standard continuum theory, which I will call the Irwin theory. Brittle fracture, furthermore, is by its nature dynamical. And this, you know, if you take something brittle, like a piece of chalk, and you break it, then you can't really do it slowly. Now, there are ways to take brittle things and break them slowly. For example, you can take glass and put it underwater and contrive to do that, but the nature of it is something that either doesn't go or goes quickly. So dynamics are an intrinsic part of this process. And the dynamical processes, again, span many orders of magnitude, because if you work it out, you'll find that the natural scale for the things that are going to come apart is happening 10 to the 8th times faster than anything you can actually measure in the lab explicitly. So 10 to the 8 spatial scales, 10 to the 8 time scales. And for this reason, I will claim that fracture is a good example of something where math is going to dominate and computers are going to come along later as a servant. I think for anyone in the audience who is young, this probably has been something you've wondered about. Has the mathematical approach to topics become obsolete? Because now, whenever faced with a problem, we'll just bring in computers and solve it by brute force, and the math won't be needed anymore. And I would say that if you take problems that have been around for a long time and were ultimately solved, the fracture problem is one which was in some ways posed recently enough that you could watch math and computers go head to head with each other, and I think math clearly won. It's not that the computers were not needed, but they were servants. They drew pictures, they did computations once the basic structure was known, but the ideas were never established by computer. And then I should say, because of the topic of this conference, that in the case of dynamic fracture at the atomic scale, the mathematical tool beyond all others that was useful was the Wiener-Hopf technique. So the detailed study of fracture at the atomic level goes back to Griffith, who worked on the problem at the Royal Aircraft Establishment here in the United Kingdom until he set his lab on fire and was ordered to stop. That cost Britain civil aviation, too bad. Frenkel and Kontarova in 1938, the first discrete model of a dislocation, which is a related singularity. The first dynamical model of a singularity dislocation, again, Atkinson-Cabrera, 65. The first atomic static model of a crack, Thompson, Shih, and Rana, 1971. The first estimates for the origins of fracture energy at the atomic scale, Rice and Thompson, 74. And the first numerical simulations of fracture at the atomic scale, purely computational, Ashurst and Hoover, 1976, done at Los Alamos, which had then, to some extent, is now the largest computers. But I would like to focus on the contributions to the atomic study of dynamic fracture, where the person who pioneered them is here in the room, Leonid Slepyan. This was a real tour de force. The first papers were written around 1980, and I think it should have been quite a surprise to anyone who heard about them that it was possible to take a collection of atoms, hook them together by forces, take a crack, drive them through this lattice, and solve the whole thing analytically. It would seem like too difficult a problem to be able to solve. I think in some ways it was sufficiently difficult and sufficiently counterintuitive that it could be done, that the only person who followed up on it for quite some time was Slepyan himself. And so there was a series of advances in these techniques. Transonic cracks the next year. The first problems had been cracks moving out of plane, so they could move in one dimension perpendicular to the plane in which they lived. But it was also possible to use the same methods, although with greater effort, for cracks moving within a plane, and that was done by 1984. And 2002, Dr. Slepyan wrapped up a lot of this in a book, Models and Phenomena in Fracture Mechanics, that brings all these results together. And I should say that he's continued to work on it since and has a steady stream of results. I still remember when these papers were faxed to me. I was abroad, and someone sent them by fax, and I read them over and over and over again. It's a wonder I can even still get a copy of the papers, because it was lousy fax paper, and I wrinkled them up in my travels. But there were more things to do, and so I'm going to both describe to you very briefly what was accomplished with those first approaches, and then talk about some of the additional things that were possible to add. We'll have to ask him to be sure, but I think in the first papers the idea was that the lattice models were a crude approximation of a material with microstructure. Because my background is physics, my point of view was, no, it's not a crude model of material with microstructure. It's a highly accurate model of a crystal, which is something all of you actually have in your pocket. If you wanted to break a brittle crystal, all you'd have to do would be to open up your cell phone, take out the processor, and break the central processing unit in half. That's a very, very high quality single crystal of silicon with a very precise face oriented on which the the electronic structures are built. So this wasn't a crude approximation. This was absolutely the right starting point for some fundamentally important materials. The algebra was fairly complicated, even in the mode 3 model, so something I'll present is a one-dimensional simplification that I think is the starting point for anyone who wants a quick introduction to how to use the techniques and doesn't want to spend more than 20 minutes doing algebra. Extended it to a triangular strip. This made it possible to begin to look at some physical phenomena, velocity gap and lattice trapping, and I will discuss those. Those were connected to instabilities, nonlinear instabilities of the motion of a crack in a lattice. That was another phenomenon that hadn't been studied that came within reach. And then today I'm going to spend a bit more emphasis on two somewhat more recent developments. One is the resolution of a paradox involving interface cracks, and the other one is the resolution of a paradox involving supersonic cracks. So here is the setting of a one-dimensional model that involves relatively little algebra that can show how the Wiener-Hopf technique applies to the solution of a fracture problem. So let me walk you through this. Take a row of atoms and connect those atoms to each other horizontally by springs of unit strength. So they just wiggle around each other, and you can get waves to propagate along this chain. And there are just two rows of atoms. There's an upper row and a lower row. The upper and lower row are connected also by strong springs, but there's a catch, and the catch is that if the strong springs stretch more than a certain amount, they break. So the force drops to 0 past a certain extension, which you can set to any arbitrary amount that you wish. The system has to be driven somehow. You have to do something to pull on it, and that is done by attaching the upper and lower rows of atoms with weak springs to a ceiling and to a floor that you pull apart symmetrically. And you make the springs weak because it's like attaching lots of other masses in series to each other. And if you attach n masses in series, then you get a spring constant of 1 over n. I just removed all those masses. So you have many, many fewer degrees of freedom. Nevertheless, this model preserves the essential structure of dynamic fracture problems solved by the Wiener-Hopf technique. So spring constant of strength 1 over n. If you wanted n to be 10 to the 12, there's no difficulty in that. It's perfectly easy to solve. spring constant 1, these springs can break, these springs, let's not let them break, let's not leave these break, and let's set out to solve this model. So here I've written it down. Atoms on the upper row are connected to their neighbors, and so this leads to a discrete version of the, let's call it the stress tensor, or the right-hand side of the wave equation. This is the coupling. The ceiling is pulling up on the masses to pull this object apart. These are the bonds that can break. That's a Heaviside theta function. So if its argument is greater than 0, if the argument is greater than 0, it's 1. If its argument is less than 0, it is 0. So this describes bonds that break. And I've added a little bit of dissipation, energy loss. This is actually necessary to tell the system which way time runs. If you don't tell it which way time runs, the math actually gets quite confused. There's singularities that will emerge in the Wiener-Hopf solution if you don't put that in. So yesterday there was a discussion of cases in which there's certain matrices that don't have factors. So immediately my mind went to terms such as this, which you might not, in this case, have thought to put in the beginning, might not thought it was essential, but if you don't, then you run later into mathematical difficulties that are actually telling you about something which in my terms is a perfectly physical problem. You have to know which way time runs for Humpty Dumpty, because if Humpty Dumpty falls down, he breaks and you can't put him back together again, and that's an asymmetry in time that the model really wants to know about. So there's one additional, if you want to solve this, of course you could do it numerically, but I'm much more interested in an analytical solution for reasons I spelled out before. In order to achieve one, the general problem I don't believe has an analytical solution, but a steady state assumption does. This is useful because it corresponds to the long time limit, hence letting you jump many orders of magnitude in time. Long time limit assumes that the system reaches a steady state. A steady state doesn't mean that there's a bubble that moves completely unchanging. What it means is that every atom does a dance, and that dance involves wiggling up and down, and then there's this time unit, and then the next atom over does the same dance, and then the next atom over does the same dance, and so this dance repeats atom to atom at specified time intervals, and that's the way steady state looks here. So the mathematical incorporation of that is to state that atom at n+1, its time behavior is the same as the atom at m, but displaced in time. That's it. So that's the way steady state symmetry applies to this system. And with the insertion of that idea, the problem is almost solvable. I say almost for the following reason. There's a strong nonlinearity here. The nonlinearity states that there's a bond that breaks when an extension passes a certain point. Very strong, very abrupt nonlinearity. To use the Wiener-Hopf technique, we're going to have to convert this to a linear problem. Now, yesterday we heard of a very beautiful way to do this with the lax pair and a solvability condition. Here, it's almost trivial by comparison. Here, all you have to do is the following. Just note that there exists some time at which the bond will break. Before that, the bond is in place. After that, the bond is not in place. And therefore, rather than having a nonlinearity that applies to the atomic positions, simply identify the time at which they move through the threshold and replace the nonlinearity in position with the nonlinearity in time. But at this point, it's simply a boundary condition of the type that the Wiener-Hopf technique is able to handle. I say it's almost trivial. It's almost trivial. Well, you'll see in a little bit that there's, in order for this to correspond to the real physical problem, not only does 0 have to be the time at which the bond breaks, but the atoms had better not have gone above the breaking point before, because they would have broken before if they had. However, as we will see, the mathematics of this will actually naturally produce solutions in which the atoms do go above the breaking point before, And checking for that, I've learned from Lev Truskanovsky, is called an admissibility condition. Is that correct? Anyway, so it's important to impose and check on this admissibility condition, something that is easy to forget because this step is so easy. So we'll come back to that in a little bit, and it's actually very important for the dynamics. It's one of the most important qualitative things that there is about a crack. So now this is in a form where the Wiener-Hopf technique can be applied. Let me just see if I'll just display the solution without much ado. You Fourier transform it in time. Once you've done so, it's a problem where the standard methods apply. These time displacements turn into exponential factors in time. They're just multiplicative. This is the sort of thing that the Wiener-Hopf technique was born to handle. Dissipation resolves singularities, pushing them off of the real axis and into the complex plane where they belong. And so the solution looks as follows. You construct this function, 20 minutes, half an hour of algebra maximum, unlike other problems which we will see later. So this is definitely an explicit solution. You form the following ratio. This is actually related to the dispersion relation of waves ahead of the crack and the dispersion relation of waves behind the crack. So with and without the break, wave motion along the chain, and a ratio of those two dispersion relations. And then a quantity of physical interest is given by this expression, which will look at least vaguely familiar to all of you with experience with the Wiener-Hopf technique. The precise quantity which is described here is the following. There exists some point which I can stretch the system to where I've stored enough energy in over to the right-hand side of the crack that there's enough energy to break the bonds. Certainly can't go before then. And so that's the natural unit in which to measure things. It's the smallest possible extension for which any motion could in principle be possible. So I measure extensions in units of that, and if I do that, then if I stick in a crack velocity v here and then just do an integral over this dummy variable omega prime, then I obtain how hard I have to stretch the system to get the crack to move that fast. So I find natural units. To measure extension, I stretch the system up, and then this says, the crack will run at this speed at that extension. And the harder you pull, the faster it runs. It's really not all that surprising. There's actually a very simple expression for how hard you have to pull it in order for it to be able to run, and it's just square root of 2n plus 1, where n is the 1 over n is the weakness of those weak bonds at the top. So here's what the solutions look like. There's first of all a static branch. So if you grab the system and you start dragging the edges up very slowly without giving anything any velocity, then you actually go way past this point 1 where there's enough energy, up to nearly 2, before the system figures out that it can move, because it's trapped in a metastable minimum. This phenomenon, this existence of a static branch, is called lattice trapping, and that was found by Rob Thomson in 1969. It's at this point that the system finally becomes linearly unstable and would begin to run no matter what. Incidentally, many computer approaches to this and similar models have gone along here and then concluded that there did not exist running solutions, and then they've gotten to here, and the system at this point is subject to a whole bunch of not numerical instabilities, physical instabilities where the crack can't run stably, and it actually will often, in a numerical implementation, self-arrest. So if you simply do numerical studies of a typical crack system by building it on the computer and then pulling on it, it's been very common to conclude from that running cracks didn't exist at all. Because unless you knew that this branch was there, you wouldn't set up the initial condition so as to find it. And the computers tended not to find it automatically. So that's an indication of the sort of reason that it's so helpful to know the mathematical structure of a problem, even in a qualitative sense, before going to a computer. And if you don't, why just using the computer in a way that looks superficially sensible can yield completely misleading results. Anyway, the analytical results that come straight from the Wiener-Hopf formula are this full black line, and I'll discuss in just a second why I've drawn a terminal point here and then indicated just this red line as the solutions that you can actually access. I have here original curves of this type from Slepyan's papers. I reproduced one of them for fun in the square lattice a while ago just because I felt like it. Any rate, these are lovely results of the Wiener-Hopf technique. This actually represents a lot of work because there's 3 different models of progressive and increasing complexity. These are not this one-dimensional model that I showed you. I'll give you some taste of the effort that it takes in order to produce these 3 solutions as I go along, because they're done with infinite numbers of degrees of freedom in infinite planes with lots of motion. So let me come back now to the point of admissible solutions. So these solutions down here, all this jagged stuff which looks so interesting, these are not physical once you impose the condition that t equals 0 is the first time at which the bond will break near the crack tip. And I have illustrated this with solutions from a very elaborate model. So this is one with infinite numbers of degrees of freedom, with cracks moving in plane. And if you solve with the Wiener-Hopf technique at a velocity that's in this region that I said is forbidden, t equals 0 is the point where, according to the math, the bond should first break. But if you look at the solution, I have this just for illustration, then you see that the bond actually went above the breaking point supposedly at a negative time, but the bond didn't break, and then it came down, and then it wiggled around the breaking point for a while, and then it finally decided to break. Now, there are macroscopic objects that could behave like that. You can stretch them too much and then bring them back down, and then they can eventually decide to go. But atomic forces are too perfect to allow that. They break the first time or they never break. That's it. So this is physically inadmissible, and for that reason, if you come back here or look at my subsequent plots, I will indicate a point at which the physically realizable solutions begin. That means that there's this range of velocities that is forbidden. You can call it the velocity gap. And I had spoken earlier about the fact that fracture is something, brittle fracture is something which tends to happen quickly or not at all. And this you could call the fundamental reason for it. The nature of the process is one, and this is literally true only at 0 temperature, but I still think even at our normal room temperatures for brittle materials, it captures the essence of the materials. The atoms don't want to permit the solution to exist when the velocities are below a certain critical value. Hence a tendency always for the crack to sit stationary, trapped, and then to figure out eventually, after lots of trials, typically driven by thermal fluctuations, that there's this dynamic branch up here, and then immediately rushing to something on the fracture of the fraction of the sound speed and rushing along. So although this is a simple model, and although there are all sorts of caveats that one could express, I think that this inadmissibility of all the low velocity solutions is actually capturing one of the essential qualitative features of brittle fracture that we've known about since we regretted dropping a glass of milk. So I mentioned that computers are servants in this game and not masters. I will be using them. One of the things I want to say is that, and I'll mention this more as I go along, the analytical solutions are really quite complicated and take a long time to put together. I was quite worried for a long time that I had made an algebra mistake in some portion of the work. So one of the things I did at one point was to do explicit numerical simulations and then compare them with the Wiener-Hopf technique. And I just display that to show that, and I'll show some other examples of that as we go along, that you can indeed, once you understand the structure of the model, set it up and find all of the solutions explicitly and even get 4 decimal point accuracy if you choose between the Wiener-Hopf technique and explicit solutions of equations of motion. So that's what's being displayed there. Now let me begin to discuss some of the physical phenomena and additional questions, paradoxes, some of them physical, some of them of mathematical character, that were possible to resolve with this tool in hand. Before I had learned of Slepyan's methods, I was actually in the lab collaborating with people who were carrying out experiments. This is work that I did with Jay Feinberg, who had just arrived as a postdoc in Austin. This is around 87, 88. He's now in Jerusalem, but he was a postdoc in Austin at the time. And we had found an instability in dynamic fracture, which manifested itself by when the crack was moving relatively slowly, 20-30% of the Rayleigh wave speed, the crack surfaces were smooth, and then they became rougher and rougher, and then the surface became very jagged. We published several papers on it calling it an instability, and the reason we called it that was that it was a perfectly good English word that covered the fact we had no idea what it was. Let's always keep that in mind. If you find something you don't understand, come up with a good ordinary English word and use it, and everyone will be happy. Actually, the essence of this instability had been understood. Wolfgang Knaus and K. Ravi Chandar had proposed a mechanism for this in 1984, which I really took a long time to realize was the same thing, but they proposed that as cracks went along, they could become unstable to sending off branches that were at an angle to their direction of motion, and they drew cartoons to this effect, which I've illustrated here in the 1984 study of crack branching in plexiglass. Now, in the context of these models, this is actually something which you can try to calculate, and the way you can try to calculate it is as follows. Carried out calculations in the triangular strip, and one of the things you can do is to compute the stretch of horizontal bonds above the crack line. And just as it paid to be very attentive to precisely when the ones along the crack line broke, now you can start being attentive to whether any of the bonds above the crack line should break, or whether they're always kept below their breaking point. And so this is something perfectly accessible within a Wiener-Hopf framework. I show here a sequence from a numerical sequence where I solved the thing, and you can actually see an instability emerging, which forms branching-like structures. But if I come back here, that's the point where the Wiener-Hopf technique says that steady states lose stability towards horizontal bonds breaking, and therefore the steady state assumption that we've been making about the dance of atoms is out the window. It can start to form branches, and this moves beyond the level at which I at least was ever able to solve anything analytically, but at least you can identify the origin of the instability in an analytical solution. So
can I just get that clear? So it's you're checking the local bonds, and then you're getting this criterion that the bonds break at some angle as well as along the crack.
Precisely. And the reason you can do it is because the nonlinearity is so sharp. So the law of interaction between the atoms is perfectly linear to the point of breakage by assumption. So you just assume that and look for the point where the assumption is no longer self-consistent, and that's the point where the instability would set in. If you look at the actual laws for interaction of atoms, of course they're not this perfectly linear until I break, but the brittle solids like silicon, it's not a bad approximation at all. So this is a reasonable starting point to understand the qualitative features of solutions. I should say that this is not the end of the story with these instabilities by any means. A lot of experimental work has been done since, and there's a variety of theoretical approaches now with different theoretical tools, phase field models and other things, but I still think this is probably the simplest way to capture an essence of the problem. So let me continue on with some additional physical examples. The next one, which I would like to present, is a discussion of interface cracks. And the applications here are to things such as friction, earthquakes, and other structures where something slides over something else. So there there's some peculiar things about the continuum solution of interface problems. Let's suppose I have a floppy solid and I build a little crack so it opens, so this is floppy, and I'll take this yellow thing to be infinitely rigid, and I take the floppy thing and I build a little gap and then I push to the side. And I ask what continuum theory says should be the nature of the elastic solution in the vicinity of the two places where there's contact. I believe that solution is due to Williams 59. In any event, I'll show you some of it later, but the essential singularity looks like this. For ordinary fracture mechanics, where you have where the two solids in contact are identical, there's a generic continuum singularity that builds up at the tip of any crack, where the opening displacement goes as distance to the crack tip r to the 1/2 power. It's a square root. But if the two solids are different and have different elastic moduli, then there is a complex correction, and so the solution is supposed to oscillate near the tip. And so it takes this form. But the thing which is puzzling about that is that then it seems to indicate that the upper solid should penetrate the lower solid, because it's wiggling up and down. Granted on a logarithmic scale, but even so, that's what it's supposed to do. So for this and for some other reasons as well, which I'll mention, the idea of studying, particularly moving things of this sort, I think was not always viewed favorably. And there were debates in the literature about whether something like this was a good starting point for studying any physical phenomenon. What I've done here, I have here a gob of undigestible details about the continuum solution, but I just want to emphasize that there do exist closed solutions that will tell you what this exponent is in terms of the wave speeds in the upper solid, which is the only thing I'm allowing not to be infinitely stiff, and also in terms of the speed. If the object is moving, if it's a moving crack, then there are corrections to the exponents, and I computed all of those too. And what I indicated here with these blue numbers, 10 to the 12 and 10 to the 6, is an estimate of how many atomic rows high a system would have to be in order for you to have to worry about a stress going through a complete cycle, or a displacement going through a complete cycle, so that the lower solid would penetrate the upper one within an estimated atomic distance. So if your system is 10 to the 6 units high, then you should just guess from continuum theory that you'd be facing interpenetrating surfaces here. If it's 10 to the 12 atoms high, you'd guess you might be facing interpenetrating surfaces, and so on. So I wanted to see if it was possible to resolve that. If solutions could actually exist with this oscillating character at the front. Maybe if you pose the question in a discrete case rather than a continuum case, the math would figure itself out and allow things like this to come into existence. I'll remind you again that I claim that fracture is a problem where unless the system can resolve paradoxes down at the atomic scale below the scale at which you're worried about continuum theory, I'm claiming that the solutions may not exist at all, like the fact that brittle fracture really does intrinsically jump from low to very high speeds, and I would say that the fundamental reason for that is below that the atoms just can't figure out what to do. So if the atoms can't figure out what to do here, you wouldn't get solutions. If the atoms can figure out what to do, then you figure the continuum theory kicks in and you can just use it. So I'll provide you just a little movie of what some of the solutions look like, because we did do explicit solutions to go along with the analytics, but then I will tell you about the analytics, which actually involved a matrix factorization of a Wiener-Hopf method. See, I paid attention to the workshop topic. The application will now exit. Let's not show you the movie. How about that? Let me restart that. Probably should have tried that movie beforehand. I think I did, and it worked.
assistant trying to help?
No. It's it's a nice movie, but it's really not essential. So let's just go on. It just shows the dance of the atoms in the front, back and front of one of these little bubbles, and I could probably bring it up in a separate viewer at the end if there's time, but I'll only do that if there seems to be an appropriate amount of time. So I'm beginning by just showing the end result of calculations, and then I'll describe the calculations in more detail. So take a block, push it to the side with a horizontal stress remotely on the top of the block, and then push down also. So this is normal force, shear force. This is a setting for static friction. And what I have with all these little dots is I have cataloged cases where we claim that little bubbles can exist and can run as self-healing cracks along the interface. The numbers indicate the lengths of the bubbles, and these things delta U indicate the amount that the bubbles close in or close up. Because the back end is actually, if it's 100 long, then the back end is plopping down at atom 97, hence creating a little pucker and allowing a little bit of slip at the end of the day. So this solutions with delta U is equal 3 result in a net slip of the upper solid of 3, and the slip pulse here, for example, is 180 atoms long. So those are these little running bubbles that we claim analytically exist. This is a close-up on all the little bubbles we found running at 8/10 of the shear wave speed. And then this is an overview of lots and lots and lots of little bubbles that we found. Every dot here represents the solution of 2 Wiener-Hopf matrix factorizations plus their joining to a continuum solution. I'll describe that in a second. And if you look at the slope of this and just ask yourself what it would look like if you were teaching an intro physics class on friction, the answer is that this is a Coulomb friction of 0.2. It says that, roughly speaking, when the shear stress is 2/10 of the normal stress, then it can begin to slide. And the picture that this would suggest is that the sliding consists of huge numbers of these little bubbles of different sizes and different lengths, which are all running along carrying little discrete quantities of slip in response to the shear stress that you have at the top. So now let me tell you a little bit about without any details about the solution. The details were actually, there's a connection to this workshop, I believe, although I may need some correction. So here's the way that this solution helped produce this workshop. It's an indirect method. Eric Gertie was a student of mine in the applied math program in Austin. He spent a good 2 years in absolute terror trying to make the math behind this somewhat rigorous with error bounds, because that was required as part of the problem. And he did come up with, I think, a good solution of the 2x2 matrix Wiener-Hopf problem that arises in this case. He used Wilson's algorithm. Now, we were worried because the conditions for Wilson's algorithm, I believe, are that the matrix involved be Hermitian. If there's any proof of convergence, our matrices are not Hermitian. And so it was a bit touch and go and depended upon skillful choice of initial conditions. But eventually we did manage to have successful factorization of thousands and thousands of these Wiener-Hopf problems, which you can verify after the fact if you get them. So he managed to get that to work, but he didn't continue in academia. What he did was he applied for and got a job at Renaissance Technologies as an analyst. Renaissance Technologies is Jim Simon's company, and I believe Simon's is one of the donors to this institute. And therefore, Eric Gertie, although his thesis, which deserves to be better remembered and is largely forgotten, and that's where all the details are located, has contributed to the Newton Institute in this indirect fashion, which I think is actually probably the theory of action for the Institute if you were to really probe deeply the way that things are supposed to work out. So I will call this not just applied mathematics, but an applied mathematician. So a little bit more on the way this had to run. If you believe in the existence of a continuum solution, then you can work out the asymptotics, which in terms of the power law, as you approach the tips. And I showed you that. It's this r to the 1/2 plus I epsilon. So view that as the outer asymptote of a solution. If you solve the Wiener-Hopf problem, then Wiener-Hopf problem tells you what atoms do, and then you go far away from it, and you get an outer asymptote. And the outer asymptote is a power law, which you then have to match. So the solution scheme was to find the Wiener-Hopf solutions at a particular velocity, find the continuum solution, find your outer asymptotes for the two inner problems, find the inner asymptotes for the continuum, match them all up, and then if we got them all to match, we would say, ah, there's a solution. And we found, thousands and thousands of these solutions, found the envelopes, and that's the story which is ultimately recorded there. So that's my report on what we did with matrix factorization and Wilson's algorithm, but it's not really been followed up on, and the consequences, as I said, were this non-intuitive one involving the person rather than the math. The final problem which I will discuss is an energy flux paradox. This comes from the continuum theory of fracture. One of the basic results in the continuum theory of fracture, which really started with Griffiths but then was dropped and then taken up again by Irwin and put in solid form by Rice, with beautiful contributions also from John Willis, who's in the audience, is an expression for the energy flux to the tip of a crack as a function of the speed of the crack. These quantities alpha and beta here are simply functions of the speed of the crack in relation to wave speeds, and Ki is called the stress intensity factor, and it's the coefficient of a square root that is supposed to be the universal singularity approaching any crack in the continuum. Now, if you look at this expression, what you will see is that as soon as the crack speed passes the transverse or shear wave speed, the factor here becomes imaginary. And if that factor becomes imaginary, then energy flux becomes imaginary. And therefore, if you look, for example, in Ben Friend's book on dynamic fracture, you will see the statement that cracks faster than the speed cannot exist. In fact, this expression goes negative at the Rayleigh wave speed. The denominator defines the speed at which waves will travel across a flat surface. So at that point, the energy flux would become negative, and that's been thought to be the upper limiting speed of a crack. But there's experimental and numerical and analytical evidence that supersonic cracks can exist. I first came across this in experiments I did with Robert Deegan, Paul Peterson, and others. They were experiments in rubber, so you might worry about whether this is there's something weird about rubber. It's particular to it, but these were crack speeds. These were the shear and longitudinal speeds in the material. I think Aris Rozakis has measured such cracks in plexiglass. Jay Feinberg has found them in gel. So I think the experimental evidence at this point is relatively solid. Also, the solution of lattice models, and I did this fairly quickly, showed it, but Lane and Slepyan had found transonic solutions back in '82. So there's evidence, at least in the solutions, analytical solutions with Wiener-Hopf of lattice models, that cracks don't care about this limiting speed. And I have here results from a paper I wrote with some collaborators in, I don't remember, 2009, showing the solid lines are Wiener-Hopf solutions. I had collaborators who solved the same thing numerically, so we got correspondence between explicit numerical solutions. There were all these supersonic branches in the Wiener-Hopf solution if we pushed it. We found those. There's an additional branch that doesn't show up. The symmetry isn't quite right. I think it's a syncopated motion that we haven't found analytically. It's probably possible to find. Might require matrix factorization, but I don't believe it's been done. So anyway, yep, supersonic solutions, no problem. You can definitely seem to get them out of analytics, numerics, and experiment. So what can explain this? What shall we make of the fact that the continuum theory seems to say that this is impossible? To solve that, a few years ago with a student, Chris Bain, I decided I would go and actually formulate the energy flux tensor and just try to look at what happens and get some intuition for how to think about this. So returned to this setting, set things up to solve it analytically. There are some dirty secrets to this, which I will. So this is just an indication of the equation of motion at some early point, and even this isn't fully accurate for reasons this thing is almost the correct expression, but not quite. And it looks a bit like that. So let me tell you a little bit about some of the secrets. Yes, I can write the solution, and this is a scalar solution, mind you. I don't need matrix factorization here. But there are these problems. So once you've done it, then you can get the solution of 5,000 by 1,000 crack problem in a few seconds. But the algebra required to do it takes months. Even setting it up with symbolic algebra, which is how I did it, you're looking at something like a 15-page long expression of symbolic algebra output fed into others. So it's a finite number of steps and a perfectly explicit solution, but it's very daunting. How many people are ever going to want to reproduce that? So that's one of the reasons these techniques are not very well known, is that compared to setting up, a multi-physics simulation with the package, the effort it takes to do something like this is just incomparably greater. And so that's one of the reasons why you'll find tens of thousands of papers on the study of fracture where people have just run the computer code rather than a much smaller literature of people who've actually made their way through any of Slepyan's papers and learned how to implement these techniques because of the human time that's required. I have posted the code for this for what it's worth, but I'm not sure that's the ideal solution. I also posted the Maxima code that I used to generate the code, but I'm not sure that's the solution to this either. So that's one dirty secret, which is in a way self-evident, but I think it's worth mentioning. And it's increasingly falling out of fashion to spend such effort on problems. The second dirty secret is that even after a removal of all the evident singularities from the problem, there's singularities at 0 at infinity that you have to remove in order to get something that can be turned over to a numerical routine to carry out these integrals. The convergence is not as good as I would like, and it's finicky, and there's a self-consistency relation that you can check. The bond at 1, the bond times 0 should equal 1, so you can check that to make sure. So you think that the solution is converging, and you'd think you'd get 9 places of precision instantly and easily, but no, that's not the case. So I was very interested in the discussions of error bounds earlier because there were these logs in them, and I thought maybe that's giving some explanation as to why the systems seem reluctant to converge. But frankly, the state of things makes me uneasy, and I think maybe if I knew better what I was doing in terms of the computation, the conversions might be better, and I might not have this feeling of unease at presenting these solutions, which I confess that I have. I'll present the pictures anyway, and then I'll be ready to close. So you get, at the end of the day, I managed to get explicit expressions for the x and y coordinates of every single atom in the whole system in time. I think that was the first time this had been done. This is more painful than finding the energy it takes to make the crack run at a certain speed. The computation's even worse when you want to find the x and y coordinate of every single atom. But anyway, we did it. So this is the way the x coordinate of the atom looks. This is the way the y coordinate looks. If this looks like 0 and then a square root, basically with little wiggles, that's correct. So that square root is fracture mechanics. This is the universal singularity. Those little wiggles are phonons. Whenever something moves in a lattice, it excites vibrations at the scale of the lattice. There's actually a mathematical condition, very simple one, that tells you exactly what those frequencies have to be, called the Cherenkov condition. And there you go. So that's the way the solution looks. And tiny little things there are what will indicate whether the solution is admissible or not. The inadmissible solutions will jiggle up just a tiny little bit, but you have to expand the scale even to see it. So this is at a sort of a normal sort of speed, like half of the Rayleigh wave speed. Let's watch what happens as we begin to head up through the Rayleigh wave speed. So we go faster, 9/10 of it, and the square root, the singularity is getting compressed. This is for a system of a fixed size. They're interesting interchanges of the limits of the size of the system and the speed, but I won't dwell on it. We get closer, 95%, 99%. This doesn't look like the square root anymore, does it? But the solution is fine. It still exists. 99.5%, 99.9%, almost nothing like the square root anymore. And now, precisely at the Rayleigh wave speed, the solution has changed character. It's going too fast now to excite any of the waves. It's just gone supersonic, so it's really leaving a sonic boom in its wake. And that sonic boom is a large-scale ringing of the whole system after it, which is really governed just by a continuum theory of large frequency of low-frequency waves. And then that, as you go faster and faster, that just speeds up. No trace anymore of the expected singularity from fracture mechanics. It's just different. I have here a photograph of a crack going supersonic in a gel by J. Feinberg, and this characteristic overshoot and then undershoot is evident there. So it's at least consistent with this picture of a large-scale ringing after the crack. And I'll close with just some pictures of the energy flux here. So this is the way energy flux looks when the crack is going subsonic. It's flowing in towards the tip, and then there are all these high-frequency vibrations being created right behind. I rescale things a little bit so I can just show you what happens as we begin speeding up. High-frequency vibrations created again, and then as you head towards the Rayleigh wave speed, you see that all of that fine-scale motion is being replaced by these very large-scale oscillations of a completely different mathematical character. Here we reach the Rayleigh wave speed, and everything's gotten all nice and smooth. And now we're just zipping along with in a completely different mathematical world. So the quick summary of the energy flux paradox is that it was based on the assumption that the square root singularity exists at all. And once you reach the Rayleigh wave speed, it just goes away. It isn't there anymore. There's a different thing. It's a very abrupt transition. The material ahead doesn't know it's coming because it's moving faster than the speed of sound, so there's no way for it to know. It can't establish the standard singularity. But at the atomic level, at least, and these atomic solutions completely contain linear elasticity, there's no problem. It finds the solution, and the cracks just move on. So I'm a minute or two behind. I wanted to finish a little earlier, but I'll just close with a few words, and that's it. So here's what you can do with the Wiener-Hopf methods in these particular cases. You can solve at the atomic scale dynamic fracture problems as unlikely as that may seem. So that means you can explore crack singularities from the bottom up rather than from the top down. I claim that lets you understand the very nature of brittleness, the tendency to move along certain planes and the tendency to be fast. You can find the dynamic nature of toughness, why it costs more to move a crack faster. You can calculate it. And then there's a variety of things which from the continuum side seem paradoxical, but the atoms sort out. Interface cracks don't self-intersect. There exist perfectly good solutions where the atoms resolve the problem. Atoms also just figure out how to let supersonic cracks go, getting rid of the continuum singularity when it suits them. But I'll close with the final words, which is that insights in this problem come from math. They come not from computers. The computers are the servants. So I encourage all of you, although I need not to continue doing the math, use the computers as the servants and don't worry too much. Thank you.
Thank you. That was a beautiful lecture. Thank you. Let's have some questions. Lenny.
What about dissipation? How it arises? How the radiation by crack could be considered as dissipation?
Well, dissipation can be entered has been entered in three different ways. If you put no dissipation in, or put almost no dissipation in, then dissipation arises anyway as radiation that comes out of the crack. So you can actually compute the origin of dissipation at a fundamental level. But you can also enter dissipation phenomenologically, and this has been done in two ways. One is an energy penalty on the velocity of atoms, and the other is an energy penalty on the relative motion of atoms. All of these are physical. Well, the energy penalty on the velocity of atoms isn't physical, but the energy penalty on relative motion is, and in an actual solid this would occur because of exciting an electron cloud. So, and you yourself have put dissipation in this fashion. All of these different cases have been solved, but I think from a conceptual point of view, the fact that you can actually compute an irreversible process is the most interesting, because those little high frequency waves means that you're actually literally computing the emergence of heat from irreversible phenomenon.
Regarding transonic flow, of course, in fluid dynamics, the transonic regime is fundamental. And there's an equation called the transonic small disturbance equation, which is derived from scratch with the correct scaling and has a nonlinear term. I wasn't quite sure. Have you got a fundamental equation which is specially adapted to your transonic regime, which captures just what you want and no more? Does it come out with what you had already?
I did publish such a thing in JMPS, and John Willis led it through. I don't believe it's ever been followed up on. So I did my best to find something of precisely that sort. I wasn't aware of the case in fluid mechanics and didn't refer to it. So let's call it a stub in Wikipedia's sense. There was a start.
May I ask a question?
Yeah.
So we know that even with the most perfect crystals, we've still got thermal fluctuations, lots of stuff which is slightly, so really, I've never seen any of our nice models, and I fully support your idea of pushing the mathematics as far as it can go. Good experiment to confirm or deny our theories. So we need to build in the randomness intrinsically, and so are you doing it, adding in some stochastic elements in it, and then ensemble averaging to get some effective Wiener-Hopf equation which can get the fuzziness into the system?
So, two responses. I carried out experiments in silicon, which was the best experimental system, and there's a whole literature on that now. So there's now reasonably good agreement between theory and experiment for the specific case of silicon single crystals, which are the best single crystals there are, although they still have oxygen inclusions and of course have thermal fluctuations. Regarding the alteration of the models, I've done it numerically. I've put in all kinds of random things, and I've studied the influence of fluctuations, but neither have I done nor am I aware of any analytical work apart from some work on subcritical crack growth driven by thermal fluctuations. So I think it's entirely possible there's much more to be done along the lines you just mentioned, and I'm not aware of progress.
Okay. So again, if anyone wants to take up that challenge for this meeting, I think there is a great future for doing that, fusing a sort of a statistical element within our analytical models to get something which is very useful.
Do you think that the problem with continuum theory can be remedied if you add heat conductivity equation and compare discrete problems with the continuum theory with additional field like temperature?
Some things, that's a real phenomenon. So there are undoubtedly phenomena that will capture. However, the particular contributions to the problem brought in by the underlying discrete structure of matter, I think, can only be captured by the discrete structure of matter. I don't believe they are captured by thermal fields or any other continuum field. So the velocity gap, for example, I don't think will come out of that. I've not seen it. I've had many discussions and some attempts to have such coupled equations without seeing that phenomenon. I think another one, which is the tendency to fracture along planes, you can instantly understand from an atomic point of view. There are natural planes in the solid, so it comes out instantly. I don't see that coming out in any other way either.
There is a trace of discreteness in continuum theory, which is a toughness. But this trace plus heat conductivity, still you think it's not enough?
Well, Yeah, so you can encode atomic information in the toughness. And of course, anything you get from an atomic theory has to be compatible with continuum theory. I mean, the continuum theory, you know, provides a universal singularity that is a perfect description at some level. So really, these are questions about why certain constraints or features of continuum theory exist. You can view it in that way. So I don't think this is a problem where there's a single right way to view it. The different views are, complementary and compatible with each other. I think maybe the thing to emphasize is that the atomic theory has an outer asymptotic that joins to the continuum theory's inner asymptotic, and you'll not get information from either of them that will tell you fully about what the other has to say.
I think we'd better move on, but could thank our speaker again. Excellent.